All right, and welcome to our next lecture in Intro to Logic and Troubleshooting. Today we're going to talk about safety. So here's a brief outline of the discussion that we're going to have today. First, we're going to look at general safety practices. Then we'll look at electrical hazards, fire hazards, and some NEC guidelines. We'll talk about what that means. And then finally, we'll finish with human errors. All right, so this is the theme for today. You are responsible for your own safety. This will come up multiple times, but honestly, this is the most important piece of advice I could give you. You are responsible for your own safety. You need to ensure that your workspace is safe, and by doing the things that we're going to talk about today, you can do that. All right, so some general safety practices. So I broke this down into 3 steps. So study the job site prior to troubleshooting. Prepare for your troubleshooting using the information you got from studying it, and then the actual troubleshooting itself. So when you study the job site, you want to identify possible hazards and then also safeguards and basically understand where everything is relative to your workspace. You also want to consider other personnel that are in the facility, and if your troubleshooting basically interferes with anything they're doing or can possibly cause a hazard to anybody else. You also want to know the standard operating procedures and the standard maintenance procedures. So these are books that are kept that basically will inform you how the system operates and then also what maintenance has been done on the system. So what components have been replaced recently, what things need to be replaced regularly, and you can use that to help you troubleshoot. And then finally, you want to identify any safety showers or eye wash stations, because if forbid there's a chemical spill, you want to be able to immediately relieve yourself and get to the eye wash station or the safety shower. All right, so then you're going to prepare for troubleshooting. So you want to get your proper tools and equipment ready, and that's including personal protective equipment. That's PPE. You want to ensure that there's proper lighting, space, access, et cetera, et cetera. Basically, housekeeping. You want to ensure that things are as tidy as possible and it's as easy as possible for you to move in and out. And then plan your process. So this last step kind of goes into here. So you want to consider the result of each action while you're troubleshooting. And you want to think about this as chess, not checkers. You want to think a couple moves ahead. Take your time, move methodically, follow your process. And last, safety is a state of mind. So this is something you really need to consider, you really need to think about as you move forward, as you do every little task. All right, so electrical hazards. So oftentimes you'll troubleshoot a component that's hot, and that means it's energized. That means electricity is either running through it or it has a electric potential. There's a hot side, there's basically a plus side and a negative side, and there's a voltage potential. And if you connect those two, if you get them close enough, you'll have arcing, or you'll have current go through. So, and just right here. So, ignition requires some sort of like hot process or some sort of spark. And so, if there is a spark, if there is arcing going through, this is something to consider too, and we'll talk about this later. But basically, what happens with electrical shock is it's electrical current that's going through your body. Over here, I have a doodle, this little GIF over here, showing the path of the electricity taken during a shock from a downed utility line. So as you can see, the electricity would come down through here, and basically you serve as a wire. So electricity goes through the ground and then up through your leg and down through the other one. And the severity of the shock depends on the amperage, path, and time. And basically we can calculate this using Ohm's law. So we can say the current is equal to the voltage, whatever the voltage is, of this wire, divided by the resistance of our body. So our body, again, from here to here, this path has some sort of electrical resistance associated with it. So the time of the sustained shock actually matters too. But over here I have a table that shows amperage in milliamps and the effect that you feel, the qualitative effect that you feel. So from 0 to 1 milliamps, you can't really feel. It's imperceptible. From 1 to 3, you can actually tell, so it's noticeable. This is where it starts to feel like there's a little buzz or something. And then from 3 to 5, it starts to get annoying or irritating. You don't want to touch it anymore. From 6 to 9, you actually start to have muscle spasms that force you to kind of grab onto whatever electrical component you're getting shocked from. And this is called the no let go, where you really want to let go, but you can't because your muscles are kind of spasming. And then from 10 plus, this is a possibility 10 plus milliamps. This is the possibility of permanent harm. So we really want to be careful about this. Lastly, if for some reason you were to vaporize copper, it has the explosive force of a hand grenade. I thought this was like a fun fact given from the textbook, but this is very rare to occur, but I guess this is something you should still be aware of. All right, so energized circuits. So best practice. So if possible, first and foremost, power it down. Power everything down you can, but it's not always possible to power everything down when you're working on it. Like I said, a lot of times you're going to be working on things that are hot. And one thing to consider too is when you do power down systems, some of them have a capacity. Basically, they hold electricity or they hold electrical power and they discharge over time. Excuse me. So they can still bite. But really, this bite is just a discharge of electrical power. So this is something you really want to consider as you work through components. I just want to point out here, these are two electrical panels. You can see the one on the left is just a rat's nest. It looks terrible. The one on the right looks fantastic. It's clean, it's easy. Now, which of these two do you think is going to be easier to troubleshoot? I mean, it's obviously a rhetorical question. I'm recording a video. There's no one here to answer that. But this is by far the good one is by far easier to troubleshoot. This bad one here is an old, it's an old array, and basically this was put together and then cobbled together with new additions over time, and they did not take the time to actually implement some sort of wire management and keep things in a good shape. So sometimes you will have to get into a system that looks like this, and you don't want to leave it like that. You want to try to leave it as close to this as possible. So use any PPE that's available, rubber gloves, boots, definitely safety glasses. Follow all the procedures. So all the procedures should be done according to proper standards. This does not follow proper standards. This may may pass an inspection, but this does not look safe. This looks nice and tidy and safe. So there's standards that are from the city, the county, the employers, um, the state. There are different entities that basically set the standards. Make sure you're following them correctly. So when you leave the work site, even just for like a moment, you want to make sure that you measure the voltage when you come back to make sure that you are still like the component you thought was hot is still hot and nothing else is hot. So you want to make sure that if you leave the job site and come back, nothing has changed. You don't know if you left and somebody flipped a switch somewhere that basically like reverses turns off a circuit and turns on another circuit or something like that. So make sure you check it every time you come back. Close any components when you're done. When you're done working, so you've actually made the repair, you want to close any components that could cause harm. And actually, you want to do this too when you're just leaving. But basically, put all the panels, put all the panels back on. Tidy up everything you're working on. Keep your workspace tidy, and leave the circuit tidy if you can when you leave. This is really important because this is probably going to have to be worked on, or maintenance is going to have to be performed, or someone's going to have to troubleshoot this in the future. And if they have to go through this, it's going to make their life and everybody that's associated with it life just a long, just it's going to make it drag. It's not going to be easy. This is not going to be fun for anybody involved. All right, so when it comes to electricity, you are responsible for your own safety. See, there's a theme here. All right, next we're going to talk about fire/thermal hazards. So this here on the right, this is the fire triangle. So in order for fire to ignite, or in order for there to be a fire, we need three things. And that's basically illustrated in this triangle. So we need oxygen, fuel, and some sort of ignition source, or heat in this case. So like you can supply enough heat such that you get to a point where you're above the activation energy and you have ignition. But you need oxygen, which is present in the atmosphere. It's about 21% by volume. And fuel, so any sort of hydrocarbon, hydrogen gas, something that you can combust with oxygen. Ignition sources, like I said, hot wires, they may arc, and hot and warm surfaces, like so hot surfaces, not in electrified surfaces, but hot surfaces. And then for this, so thermal energy, so injury, it says can occur at 100 degrees C. So this is pretty high. You can get burned. So it depends on the time, but you can get burned with definitely close to 110 degrees Fahrenheit if you have that sitting on. Basically, if you're in a hot tub long enough, you can start to burn tissues. You can have like tissue damage. So this is pretty high, but this is I think also like an instantaneous value. So this is the temperature at which like almost instantaneous harm starts to occur. All right, so next we're going to look at this NEC 500, NEC 505. So NEC is the National Electric Code. So this is basically a way that um, that the National Electric Code Committee has chosen to classify and like hazards in the workplace. And they do this with a hierarchy. So they have first a class, then a division, then a group or a zone in the case of NEC 505. We're going to focus on NEC 500 today. All right, so classes. So the classes identify the type of substance. If we look over here and down here, we have class 1, class 2, class 3. So class 1 is flammable liquids, gases, and vapors. Class 2 is flammable dust, and class 3 is flammable fibers. So each of these will require a different approach when considering what to like bring for PPE, and also what to consider if there is an actual fire. So we're going to fight these fires differently. Divisions. So the divisions identify the probability that a flammable substance exists. So division 1, there exists flammable fumes or materials constantly in the workspace. Division 2 is abnormal conditions exist if the flammable material is present. So typically it's not present in the division 2 like facilities, and it's abnormal if it is there. Kind of interesting wording that they chose. Finally, groups. So the groups identify specific substances. So if you look here, A, B, C, D, so these are gases. Really, some of these are liquids at room temperature, but they're volatile, meaning that they basically vaporize, and there's constantly a vapor stream occurring at room temperature. And then down here we have dusts and powders. So you see it goes everything from metals, coal, to flour and grain. So it really does consider almost everything in here. All right, so when it comes to hazardous and or flammable substances, you are responsible for your own safety. You need to make sure that you check the NEC 500 or you check something comparable and you prepare for the job site in the correct manner. You have the proper PPE and the proper tools to tackle that job. All right, lastly, we have human error. So all humans make mistakes. So the book calls this slips. And really, this is just simple mistakes. And this is due to like really anything. So everybody makes simple mistakes. I make mistakes all day. First time I filmed this, I spelled safety wrong on the intro slide. So that's funny. But basically, this happens because we're not paying attention, or we're paying attention, but we're dialed into something else. We're calling this autopilot. And this just cannot be fully avoided. Humans are imperfect by nature. And so this is something that we just kind of have to deal with. These accidents just occur because humans are innately imperfect. One reason that this can occur, a human error, is just a lack of knowledge, and this can be avoided. So if a mistake occurs because you don't know something, because you're unaware of a system or a procedure, or how to troubleshoot a component, this can be avoided. So this lack of information can definitely be avoided. If you're unsure of something, ask, and if nobody around you knows, then do some research, figure it out, follow the 7-step method. And then lastly, your mindset. So this is something where, if you're tired or you're fatigued, or, really you're not taking the time to go through all the steps, this is where mistakes happen. And this is also something that can be avoided. Lastly, the trying or slash assigning impossible tasks. So sometimes you'll get to a point where you realize the engineer or the person who's not necessarily operating or working on this component or working on this facility or the system wants you to do something that's really not physically possible. So there is typically, not typically, I guess there is oftentimes a um, a discontinuity between the communication from the engineers and the actual operators or machinists or something like that. This is equivalent to, like, I think of somebody drawing up a component, handing it to a machinist, and the machinist being like, dude, I don't know how the hell to make this. And so that's something that just happens. Sometimes people who aren't necessarily hands-on people will think of an idea that's just not physically possible. All right, so in general, you are responsible for your own safety. Uh, you know, Again, this is the theme here today. In general, you're going to make mistakes, but if you consider safety and you really think about how you're going about things, then you should be fine. The hazards in the workplace should be kept to a minimum. All right, so a summary. So basically, troubleshooting is not the same as maintenance. Maintenance is performed to avoid a failure. Troubleshooting occurs due to a failure. And safety is vital, and this is something that really constantly needs to be considered because you're going into a situation where a failure has occurred. You don't know what the root cause of the failure is until you actually dig into the system. Housekeeping and planning make for safe troubleshooting, so keeping everything in order and following a methodical process will keep you safe while you're troubleshooting. Wear any PPE, read all the literature, follow the proper standards, and request any necessary permits when troubleshooting. And last but not least, you are indeed responsible for your own safety. Thank you very much, and we'll talk to you soon.